Hello. Today I'm going to discuss linear harmonic oscillator. So this linear harmonic oscillator problem we can discuss into two methods. One is a polynomial method, or this polynomial method we can call Schrodinger method. And one more method is operator method. In that operator method, we can use A and A diagonal operator. Then we can solve uh, linear harmonic oscillator problem easily compared to polynomial method. This is polynomial method. I already derived the total equations and entire explanation. So linear harmonic oscillator, right? The problem of linear harmonic oscillator is of importance since many systems of interest can be approximated to it. Its potential energy at V equal to 1 divided by 2 h cross square. So the K is the force constant. It is a continuous function of x. Okay. So the potential energy is constant over the region. So let us assume a particle of mass m vibrating under the influence of force, so directly proportional to its displacement x from equilibrium position. So then F equal to minus kx we can get. For conservative fields we can write and del cross F is equal to 0. From that, F force can be expressed in terms of potential energy. We already know F equal to minus kx square, where k is the restoring force constant. By using these two equations we can get the potential energy simply. So if we use this potential energy in Schrodinger wave equation, so this is Schrodinger equation, right? This is Schrodinger wave equation. So I need to modify this k function in terms of classical form. See, classical vibration frequency of a harmonic oscillator V naught nu is equal to angular frequency divided by 2 pi equal to 1 divided by 2 pi root of k divided by n. The angular frequency omega equal to root k divided by n. From this equation I can get k is equal to m omega square. So try to put k is equal to m omega square here, then you can get 1 divided by 2 m omega. So this wave, this potential energy I'm going to use here. Okay, then I can get this solution. Then if you multiply 2m divided by h cross square first here, next here, then you can get these two steps. Okay, so now here I'm considering one new symbol, that is this alpha I am considering here, m omega divided by h cross square, and lambda I'm going to consider 2m divided by h cross square. This portion I'm going to lambda considering this is quite m omega divided by h cross square. Then the remaining equation become like this. So exactly d square divided by dx square and lambda minus, because 2me divided by h cross square I'm using lambda. Here m square omega square h cross square is there. So alpha equal to I'm using m omega divided by h cross square. Then this one is alpha square, x square already there. This is the next step. From this equation, in case if I multiply here the alpha divided by alpha, here divided by alpha, then what we'll get here, this alpha is going to cancel. Then we can get this equation. Okay, d square psi divided by alpha dx square plus lambda divided by alpha minus alpha x square wave function equal to 0. Here is the very important, tricky, desirable function. This is one function xi, like this. This is xi. Xi equal to root of alpha into x. This x is there outside the root. Okay, this is I'm going to consider. So let us, I'm introducing one new function here. Okay, for simplifying this equation. So then I'm going to differentiate this thing, d xi equal to root alpha into dx. So we already got this equation, right? In terms of alpha into dx, I can use this one, right? D square, right? See here, d psi square equal to alpha into dx square. So alpha dx square, in place of alpha dx square, I can use d psi square, which is why I'm using here d psi square, plus lambda divided by alpha minus, see here, alpha x square is there. This one, right? Square this one, psi square equal to alpha into x square, right? Alpha into x square plus I can get xi square, which is why I'm using xi square. Okay, that is good. Here is a good explanation is there. Here our desirable function. So this is our new desirable function, right? So this is wave function psi of xi. It is not function of normal thing psi of x. Okay, this is one dimension, right? It is a function of xi. This is our new desirable function, right? So what are the condition of wave function, acceptable wave function? Wave function must be continuous, single valued and finite throughout the region, right? So this wave function is satisfied this equation number 1, throughout the region the value of plus infinity to minus infinity for xi, then only it will acceptable wave function. Okay, for example, for the large value of x, here I'm using large value of x, I mean xi square, lambda divided by alpha less than xi square. In that case I'm going to ignore this term, then I can get d square psi divided by dx square. This is very important condition. So this is second order differential equation, right? The solution of the second order differential equation is wave function psi is equal to some constant to e power plus or minus psi square divided by 2. This is the solution. Here is very important. Here two solutions are there. One is wave function psi equal to some constant into exponential plus psi square divided by 2 minus psi square divided by 2. So two solutions are there. One is psi equal to c e power plus psi square divided by 2. Another one is psi is equal to c e power minus psi square divided by 2. Which one is acceptable function, acceptable solution? So see here, I have already explained this thing. Since the positive solution leads to infinite value of function for large value of psi. So therefore, our acceptable wave function, one of the property is finite, right? Therefore, the only acceptable function is minus, which is why I'm using wave function psi is equal to minus psi square divided by 2. So this is not the acceptable function. This is the acceptable function. Acceptable not function, acceptable solution. Yet two solutions are there. One is plus, another one is minus. This is the reason. I am taking minus psi square divided by 2 instead of plus r. Okay, so far so good. In place of c here, c is there, constant. In place of this c, constant c, I am using h of Hermitian, h of psi. Okay, this is the solution. I'm going to substitute this solution in equation number 1. This is equation number 1, right? This is already equation number 1. See here. This is the equation number 1. In case if you try to substitute this thing, what is that mean? You want to differentiate this wave function d, wave function psi, into d psi one time, okay, and second time also, two terms. Then you can, this resultant value to substitute here. You want to substitute, okay. Then this wave function is there, right? Wave function h of psi e power minus psi square divided by 2 you want to put here. Okay, so I'm going to write this function d psi square plus lambda divided by alpha psi square into wave function psi equal to 0. Two times you can differentiate with respect to psi. The resultant value you can substitute here, and this wave function is substituted here. Then you can simplify this equation. Then you can get equation number 3. Okay, so it is look like a Hermite differential equation, right? Hermite. Hermite differential equation. It is not exactly Hermite different. This is similar type of Hermite differential. This is the exact Hermite differential equation. Okay, so then by using this Hermite differential equation, we can calculate the nth term, and you can calculate recurrence relations. Then finally you can get the polynomial solution. From that polynomial, you can find the eigenvalues, right? So that is very long process, which is why I am going to very shortcut method. So here, if you try to observe here, all the terms are similar. Only last term, third term is different, lambda divided by. Then I'm going to add these two terms like this. Okay, we want to find eigenvalues of harmonic oscillator, right? So it's simple. Then you can use lambda value and alpha value. Then you can get this energy value here. This is the eigenvalues of a harmonic oscillator. So very important. Eigenvalue of harmonic oscillator is equal to n plus 1 divided by 2 h cross omega. So from this equation, I'm going to give some important points. One is the number 1 point is the lowest energy of oscillator is obtained by putting n is equal to 0. This one. If you try to put n is equal to 0 here, then you can get n is equal to 0 here. This equation, right? N is equal to 0. Then you can get h cross 1 divided by 2 h cross omega. This is the ground state energy, or the 0 point vibrational energy of harmonic oscillator. And second point is the eigenvalues of total energy is depend on only one function. I mean one parameter, that is n, right? It depends only n. So remaining all things are constant. Therefore, all the energy levels of the oscillators are non-degenerate. Non-degenerate. First, we need to know what is degenerate. We know px, py, pz orbital, right? This is px orbital, py orbital, pz orbital. First, I am going to tell you what is degenerate. what is non-degeneracy. Here the px, py, pz is there. All the energy state is different, but wave function, sorry, all the energy states are same. All the energy states are same. P. Wave function is different. This is x, this is y, this is z. Then we can call this type of situation, this type of energy levels are degenerate energy. In case p orbital is there, s orbital is there, right? S orbital energy, that is non-degenerate energy, non-degenerate energy level. Okay. What is that mean, non-degenerate energy level? Each energy states having only one wave function and one eigenvalue. Here the wave function is the different, eigenvalues are same. In non-degeneracy case, wave function is same, eigenvalues also same, which means for example one state is there, S state. So here the wave function is same and the energy values are also the similar kind of, each energy states having the one, I don't know, one energy level, one wave function. There is no two energy levels, two wave function. That type of energy state we can call non-degenerate. Okay, so this is how I understand this degeneracy and non-degeneracy. I'm not going through the textbook definition here, degeneracy and non-degeneracy, because in case if you try to solve the CSRA and attend exams, you need to understand this degeneracy and non-degeneracy very well. So degeneracy will split into, in case if you try to substitute any magnetic field, electric field, plus 1 by 2 is there. In case if you put a magnetic field, electric field, this energy level going to split. And you want to calculate again a perturbation. So all the perturbation we're going to consider, right? Variation of potential energy, that is very, very important. For that reason, you need to understand what is a degeneracy and non-degeneracy values. Okay. So these are the energy levels of the harmonic oscillator. N is equal to 0. So this is curve because of V is equal to 1 divided by omega square x square. This parabola curve. This is horizontal. The energy difference between any energy levels are same. So in case if you take this energy level, I mean, what is the difference between these two energy levels? One is 3 divided by 2 h cross omega, another one is 1 divided by h cross. The total difference is h cross omega. So in case if you try to calculate any energy levels, if you take any energy levels of this energy difference, you can get the energy difference of energy levels h cross omega divided by 2. So these are the wave function of a harmonic oscillator. So we already know one equation, right? One equation we got, right? Equation solution. See here, this equation. Similar equation is there. Instead of that n, I am using here one function, n, normalization function. In case if you want to solve this normalization function, then you can use this normalization condition psi star psi. Then you can get this normalization constant value. So this is the procedure how to calculate normalization value. Finally, you can get the normalization constant value. This is the nth state wave function of a harmonic oscillator. So here I want ground state wave function. So here 2 power n is there, n factorial. If you try to put n is equal to 0 here, we can get 0 in place of n. I'm going to use 0 factorial. Here n. These are the Hermite polynomial. Hermite polynomial. You can use for example, h0 of x is equal to 1, h1 of x equal to just wait, I forgot this one. Mm, yeah, just right. At least I can a few one or two Hermite polynomials. Okay, first polynomials. This is h0 of x equal to 1, h1 of x equal to 2x, h2 of equal to h2 of x equal to 4x square minus 1. Okay, we can use this one. Then in case if we try to use here n is equal to 0, this term is going to 1. This is 1, if 2 power 0 1, this is 0 factorial 1, then we can get ground state energy. The ground state energy, right? Ground state energy. So like that you can get n equal to, I mean, psi 1 of x value, psi 2 of x value, psi 4 of x value, and so on, psi n. This is the psi n value, psi n of x value, psi n of psi value. This is the final eigen function. So by using this equation, I'm going to conclude this topic like this. So these are the energy levels. This is the first energy level, right? This is the, I mean, probability. This is probability density. By using these two graphs, I'm going to here three graphs are there. So first graph, this is the first graph, right? This is the probability. The energy level Cn and wave function psi n of lowest four energy levels. Okay, this is the energy level, only this one, the energy levels of the harmonic oscillator. This is probability density, psi n of x modulus square. That is the probability density. So probability density is always positive. In case if you observe here clearly, the maximum probability is at x equal to 0. That means mean position probability is maximum here. At extreme position probability is minimum here. This is quantum mechanical case, which is why p equal to here maximum at x is equal to 0 mean position, p equal to mean probability is minimum at extreme position. This is quantum mechanics. Then in case if you try to increase this numbers value, n is equal to 0 1 2 3 and so on up to n, this type of wave function you can get. This is wave function psi is equal to 60. If you observe here clearly, the probability is quite opposite to compared to quantum mechanical case. Here the probability is maximum mean position. Here the probability is maximum at extreme position. See here, this is the maximum, right? This is the maximum. This portion is maximum. The minimum probability I can get here, the mean position is quite opposite. See clearly here, the probability of particle, especially in quantum system, if you try to observe the lowest energy level, you can understand here the probability is maximum at mean position, probability is minimum at extreme position. This is quantum mechanical case. The quite opposite case is like this, probability is minimum at mean position, here the probability is minimum at extreme position. So this is how the connection between the classical and quantum mechanical is. So in case if you can't understand this thing, I'm going to explain very simple way. This is simple harmonic oscillator. This simple harmonic oscillator, I'm going to apply some force, going to oscillate like this. So what is the maximum catching point of this oscillator? This is the maximum because few seconds it will stop here and return back to return back. It will get some oscillations like this. Okay, simple harmonic oscillation, simple pendulum. So probability of catching this mass at extreme position is maximum because a few seconds it will stop here, then it will return back to get oscillations. Here we can get maximum probability, here we can get minimum probability. That is the exactly case we are observing here. So this is how this quantum mechanics and classical mechanics connection is happened. So this is all about harmonic oscillator problem. So this is the one of the method, especially polynomial method, or we can call this method Schrodinger method. So in case if you can't understand any step derivation and explanation, anything, any word, please try to comment below. I will try to reply your doubts and clarifications. So next class I'm going to discuss same problem operator method. Okay. So after that I'm going to discuss some CS array problems related to all these four problems. Till now we discussed the four problems. One is finite potential, infinite potential well, step potential well we can still now I can't discuss potential barrier I discussed. Fourth problem is harmonic oscillator. Okay.